Hello and welcome to an introductory lecture on computation tree logic, CTL for short. Much of this lecture is self-contained, but some parts of it will assume that you've already digested the introduction to LTL lecture. CTL, which again abbreviates computation tree logic, is a logic introduced by Clark and Emerson in 1981. These are two other Turing Award winners. We have quite a few in this module. In 2007, together with Joseph Sifakis, Clark and Emerson received the Turing Award for, and I quote, their role in developing model checking into a highly effective verification technology that is widely adopted in the hardware and software industries. CTL is an alternative to LTL for software and hardware verification that enjoys some advantages compared to LTL. First, as we'll see, it can express some properties that LTL cannot, though the opposite is true as well. Also, like LTL, CTL is automatically model checkable, and its model checking algorithm is more efficient than that of LTL. Without further ado, let's define CTL. As usual, we start with syntax. There will be many similarities with LTL, so it's useful that when you watch this lecture, you've already gone through the introduction to LTL lecture. Just like for CTL, we fix a set of items called atomic proposition, or atoms for short, and we mostly write A, B, C, etc. to denote atoms, though sometimes we use other letters or strings when suitable for specific examples. CTL formulas are built starting from atoms and applying two kinds of logic connectives. First, there are the usual propositional connectives, not or negation, or disjunction, and or conjunction, and implies or implication. These are exactly the same as for LTL. Then there are the temporal connectives, which, as you can see, are more complex and in larger number than those for LTL. Each CTL connective consists of a so-called path quantifier, which can be either for all, or there exists, and an LTL-like logical operator. You can recognize next, eventually, always, and until, which are familiar from LTL. Note, however, that in CTL, the path quantifiers and the temporal operators always come in pairs. They cannot be detached. We have for all next, there exists next, for all eventually, there exists eventually, for all always, there exists always, for all until, there exists until. The reason why for all and exists are called here path quantifiers is because used in a CTL context, they represent universal and existential quantification over all paths starting in the given state, as we'll see shortly when we look at semantics. In terms of precedence of the operators, which is relevant for disambiguating cases where we omit some parentheses, we apply the same convention as for LTL, which is actually quite a well-established convention throughout logic and programming languages. Namely, unary connectives bind more strongly than binary ones. However, since the CTL temporal connectives have a heavier syntax, we usually take no chances and we use a fully parenthesized notation. Here are some examples of CTL formulas. This is for all always, B implies there exists until C. This is there exists until A, there exists eventually A, there exists until B. This is A for all until there exists eventually B. And this is there exists eventually, there exists always A, implies for all eventually B. Note again how the path quantifiers and the temporal operators come in pairs. For all always, there exists always, there exists until, there exists eventually, there exists until, and so on. In fact, such a pair of a path quantifier and a temporal connective should be regarded as a single identifier for a CTL connective. In CTL, for example, we don't have a separate there exists, a separate for all, or a separate always. What we do have are two distinct connectives. There exists always and for all always, for example. So the following are not correct CTL formulas. This one, let me use red. So this one is not correct because we can't have a separate always. This one is not correct because we can't have a separate for all, and also we can't have a separate always. This one is not correct because we cannot have a separate eventually, and also we can't have a separate until. And this one is not correct because we can't have a separate until.